In this slide, we will be learning about the bracketing method for optimization. And for that, let's first compare the root finding method, which is the bisection method, with the use of the bisection for optimization. Basically, you know that in the root finding, we will find x which makes the fx equals 0. So for that, we were firstly guessing two initial values, a lower bound and upper bound, because it should bracket the root, and we calculate a midpoint in the bisection. And by this midpoint, we get to the second iteration. So this is the lower bound, upper bound, and the midpoint gives us an estimation of the root actually. And the multiplication of the lower bound and the function value of the midpoint, if this is smaller than 0, then based on that we make a decision of having, okay, change the upper bound. Then if this is greater than 0, then change the lower bound, and then we go to the second iteration. A similar idea exists for the optimization as well, but the difference is that we are finding the minimum instead of finding the root. And we start again with the two initial guesses, x low and x upper bound. Here you can see an example. And however, these two initial guesses may not be sufficient, because in the first iteration here we will have lower bound, upper bound. This is somewhere in between, but where is it? We really don't know that. That's why we will need two more points within the interval. So in addition to the two initial guesses, we will have additional two more points. And with these two more points, we will check whether the minimum occurred within the first three or the last 3 points. So let's say we have 3 and 4 points. We will check first 3 if minimum is here, or the last 3. We will check those and see. Here actually is defined as L1 and L2 are the ratios of the, for example, first 3 and the last 2. And that the ratio is important, the L2 divided by L1 and L1 divided by L2. So, and the L0, which is the difference between the lower and upper bound, is actually L1 plus L2. So we have this ratio of L1 divided by L0. This is L1 divided by L0 and L2 divided by L1. And in here, if we replace this into here, we will get actually a formulation. And in this formulation, we use golden ratio to be able to add these two more points to the interval. So those are not a random point, but we can have a logic of having golden ratio. That's why let's see this golden ratio in the following slide, and then continue to develop this approach of bisection for the optimization. In this slide, we will talk about the golden ratio, and the golden ratio actually is a mathematical number that we calculate by root 5 minus 1 divided by 2, which gives us 0.61803, and it continues like this. And this ratio is very important. Actually, even in the human body, there is the golden ratio from the nature. And this golden ratio is important to have a pleasing view to the human eye, let's say. And that's why, for example, in the ancient Greek, because it is considered pleasing, a rectangle with golden ratio was used. You can see the longer edge is 1 and the shorter is just this golden ratio, 0.61803. And these Greek constructions were made based on this golden ratio to have a pleasing view. And it comes also from the Fibonacci sequence. You know that the Fibonacci sequence has the summation of first two to have the third one, and it goes that way to be able to have all the numbers. And the ratio of consecutive numbers goes to the golden ratio. You can see that 0 divided by 1 here is 0, 1 divided by 1 is 1, 1 divided by 2 is 0.5, 2 divided by 3 is 0.667, 3 divided by 5 is 0.6, and then you can continue like 5 divided by 8, 0.625, 8 divided by 13, 6, 0.15, and if you continue, 13 divided by 21, and if you continue, it goes and converges to this value of 0.61803. So we can say that the golden ratio can come from the Fibonacci sequence as well. So this golden ratio is used to be able to identify the additional points in the golden section search or in the bisection algorithm. And because we are using golden ratio, the bisection algorithm in the optimization is called the golden section search. And in here, if you remember, we said that we can have a ratio between these L values. In the previous slide we mentioned that. Let's write it down here. And L1 divided by L0, and L0 was L1 plus L2, and this was equivalent to L2 divided by L1. We have this ratio basically, and from this ratio we can say L2 divided by L1 is R value. So we want to have this ratio of L2 divided by L1 as the golden ratio. We can say this is R, golden ratio, and that's the 0.61803. So different ratios can also be used here, but we want to use the golden search or golden ratio to be able to have a logic to continue on the function. And when we set this as golden ratio, then we will have here if we modify this a little bit or organize this, let's say based on the golden ratio, we will have here, for example, this is R, and this is the opposite of it. Actually, let's first of all reverse these two. Let me write it down again. If we have here L2 plus L1 divided by L1 equals L1 divided by L2. So this is just the reverse of it. And from here we can have, you can see on the left hand side, L2 divided by L1 plus 1. Actually, L1 divided by L1 is 1. And on the right hand side, it is just L1 over L2. And this is R, and this is 1, and this is 1 over R. We can write this way. Or if we modify this, so let's move this R here and try to have a function that becomes R square plus R minus 1 is equivalent to 0 when we modify it. And we can solve this using the root solving approach. If you remember, the results can be obtained as the minus b, which is 1, plus in root square 1 minus 4 minus 1 divided by 2. 2a, a is 1, here is 1. So from here we will have the golden ratio as root 5 minus 1 divided by 2 is equivalent to 0.61813. So basically what we do is we said here it will be golden ratio, but actually it comes from this ratio anyway. So the ratio over here that we have actually here, that we have from the function, adding 2 more points and having this assumption of this division will be R, then reversing this and having a function and solving it will give us the golden ratio. That's why this R value as a golden ratio is a perfect movement in the optimization. It comes from the ratio of here having 4 points initially, and this golden ratio will be used in the golden section search. Now in the golden section search method, we will start with 2 initial guesses which represent the lower bound and upper bound, which will bracket one local extremum. So there can be a minimum or maximum, doesn't matter. That's why it's called extremum. It has to bracket it. Then, as the third and fourth points, those will be interior points, x1 and x2. We will choose those according to the golden ratio. And for that, we will set this d value here on the graph, for instance. The difference between xl and x1, d, will be defined as d is equivalent to the golden ratio, root 5 minus 1 divided by 2, and the difference between xu and xl, lower bound. And from here, we simply obtained a d value from this formulation, you can see, and we will use this d to get the x1, and x1 will be x lower plus d, and the x2 will be x upper minus d. So basically we have just this formulation, multiplication of the golden ratio by the difference of xu and xl, and then we will have, so this is the d, that's why we will have x1 minus xl equals d here, and x2 minus xu equals d here. And these formulations will be used to get these x1 and x2. Basically, that's why we don't need 4 initial guesses, we just need 2 initial guesses, and the golden ratio to get the additional 2 values, x1 and x2. Then what we will do is, we will calculate fx1 and fx2 because we know the function value, and 2 results can occur. The first one is, the x1 function value can be smaller than the x2 function value, then fx1 is minimum. This is the assumption. So here maybe we can check the function value of x1 and function value of x2. x1 is smaller, so that means this is the minimum. And the domain of x to the left of x2 here, in that case, will be eliminated from xl to x2. Here, this part then will be eliminated because this was found as the minimum. Then we can just set, okay, this x2 then is larger, and we can just remove xl and make the new xl as the x2. So that's why we make x2 becomes the new xl for the next round, and we set this as xl in the second iteration. This is the second iteration you can think of, and again we will have xu as the constant here. In other scenario, if fx2 is smaller than fx1, this is the opposite of this, then fx2 is minimum. In that case, we will just eliminate the other part, because then the domain of x to the right of x1, from x1 to xu, will be eliminated because fx2 is minimum. It is not seen here, it is a different case, so I'm not able to show in the graph, but assume that this minimum was found as the x2, then we will remove this part and set xu as x1 as xu, and set it as the xu in the next iteration. And that's why x1 becomes the new xu for the next round. So 2 scenarios, we can simply use them to get the minimum. And the benefit of the golden ratio is that because the original x1 and x2 were chosen using the golden ratio, we don't have to recalculate all the function values for the next iteration. So here you can see we already have the function value of this lower bound, and upper bound was the same from the first iteration, so we can continue with that. Then here we will create another x1 and x2 using again the golden ratio, and continue to the iterations until the results are converged. So this is the basic idea of the golden section search method. In the following iterations after the first iteration, because we already know about the xl and xu, we just need to determine the new x1, and this is done with the same proportionality as before we defined, and it is basically, we can say we can use this x1 is equivalent to, sorry, x1, it should be x lower plus root 5 minus 1 divided by 2 xu minus xl, like this. And a similar approach would be used for the alternative case, where the optimum fell in the left subinterval, or right. So for the left and right, we can use the same idea and have the results. With the repeated iterations, the interval containing the extremum is reduced rapidly by a factor of golden ratio, which is about 61.8% at each iteration. So this is very efficient. That means after 10 rounds or iterations, the interval is shrunk to 0.618 to the power 10 or 0.008 or 8% of its initial length. And after 20 rounds, it's about 0.0066%. So it is very accurate after 20 iterations. This is not quite as good as the reduction achieved with bisection actually. In the bisection it's 50%, but here the reduction is maybe lower. But still, because this is an optimization problem, this is more difficult because we want to find the root of the derivative without using derivative. That's more difficult. That's why the optimization is harder than the root location. That's why maybe this may be less efficient than the bisection used in the root finding, but still we can find the root, guaranteed root, with the golden section search method as well. That's the good advantage. Of course, we can reach to the local minimum or maximum instead of global. That's why we need to try different initial guesses and see if there is any other global minimum or maximum.